Okay, we're going to take a look at combinations in this video and compare them particularly with permutations. And just a quick review, permutations, as you know, depend on the order at which things are presented. So order matters in permutations. And we looked at a lot of variety of questions relating to permutations in the previous unit. Now, today we're going to take a look at combinations, and particularly see if we can determine the difference between the two. And the big difference is that for combinations, order is not important. And what does that mean? Well, let me just go through some examples here. If I take a handful of stickers, let's take 3 stickers, and I use them to try to illustrate the difference between the two permutations and combinations. If we say take 3 stickers, and I decide to, let's just take 2 of these. So we'll permute 2. So 3 P2. So permute 2. We know that what that means is I can basically, out of 3, I can take these 2. All right? We know also we can flip those. So that's 2 ways. And then I can take these 2 and spin these. That's another 2 ways. And then I can take these 2 and spin them. And that's another 2 ways. So that's a total of number of 6 ways, or 6 arrangements, especially when we're considering the order matters. Now, for combinations, a little bit different. Combinations, the order is not important. So, for example, if we take out of these 3, and we choose 2 of the objects, 2 of them, the rocket and the spaceship, it doesn't matter as far as combinations are concerned whether they're this way or this way. Of course, that means you've reduced the number of combinations significantly compared to the number of permutations. So really, it's like, well, how many of these items can we put together? Period. Well, you can put these 2 together, that's 1. You can put these 2 together, that's 2. And then you can put those 2 together, and that's 3. So there's 3 ways. Now, interestingly, when you look at this, if we look at the formula, 3p2, that's the same as saying, well, n factorial over n minus r factorial, and that should equal 3 factorial divided by 3 minus 2 factorial, which equals 6. Now, on the other hand, talking about combinations, we only have 3 potential ways. So we'll keep an eye on this and see how, if we can relate this number and this number somehow, and also when we're thinking about the R value as well. So we'll keep that in mind. We've got 6 permutations, 3 combinations with 3 stickers, and we're choosing, of course, 2 each time, whether we're picking them as combinations or permuting 2 of them at a time. So let's take a look at that for 4 stickers. Now, for 4 stickers, let's choose or permute 3 of them. So let's do that. So 4 permute 3. And we'll just divide this up on this side. Combinations. Well, 4 permute 3 you can think of it as, well, here's our 4 stickers. And we know that if we take one of these, we can take these 2 and bring them down. And we can flip those around. And we can change the order of these in the front. And these are all different because the order keeps changing, even though it's the same objects. And so we know how to deal with that. And that is just simply 4 factorial over 4 minus 3 factorial, which is just simply 4 factorial over 1, which is 24. But if you take a look over here, now I'll introduce the notation for combinations. Instead of using P, you probably would expect to use C, and you'd be right. So if we say, okay, we've got 4 stickers, and we're going to find out how many combinations we can make if we choose 3 of those stickers. So subtle difference, just obviously the letter is the difference. So we'll move those stickers over here and say, okay, we've got 4 stickers, we're choosing 3 of these stickers, and the order doesn't matter. So once they're together, that's a combination. Whether they're in a different order, it doesn't matter. So let's say I take the rocket ship first, and then I take these 2. There's one combination, and I can take this back and bring this person down, the astronaut, and that's another combination. And I can bring this guy up and bring this guy down, the actual planet, for another combination. Now, that's it for the number of combinations we can have with 3 other items with this rocket ship. Now, bring this back up. Let's say we bring this spaceship down. We've already had a combination with the rocket ship, so we don't want to bring that back down again because we've already gone through that. So that leaves only these 2 left, which is 4. 4 ways, 4 combinations. If I start bringing this back down, we've already kind of covered that already. We've already put the rocket ship with all the other ones already. We've already taken those combinations already. So that's it. So 4 versus 24. And again, if you take a look at the R and you compare that to the previous example, it's like, well, 24 divided by 4 is 6. How does 3 relate to 6? Well, quite possibly 3 factorial could represent that difference. And in fact, if you did it again, you might want to pause the video and try it with 5 objects just to see if this is actually true. Now, pause the video and give that a try. I'll just keep going. Now, it is true. For our combinations, we basically are discounting or getting rid of the fact that you can rotate or change the order of those objects. So when you think of a combination, we can think of it as, well, it's really NCR is really the number of permutations of those objects divided by R factorial. And we can expand that to say NCR, or N choose R, is equal to N factorial over N minus R bracket factorial times R factorial as well. And that's our general equation for combinations. You can see that we're dividing out all those combinations of those elements that we've chosen to put in or chosen to combine together. We're sort of dividing them out, which makes sense because you don't want to have permutations within that. You end up with too many combinations. Remember, the order doesn't matter. So I'm going to pause now, and I'll upload another video just going through some examples.